Hi everyone. In this video, we're going to go over conditional probability and we're going to define independent and dependent events. So to start, suppose we have an experiment that we conduct 2 times and we let A and B represent 2 possible events from the experiment. Now sometimes the outcome of the first trial will have an effect on the outcome of the second trial. In such a case, we have the following definitions. So the first definition here, we define what is called a conditional probability. Now, this notation here is read the probability of B occurring given that A occurred previously. So this little bar right here means given that the event A occurred previously. So once again, this is the probability of event B occurring given that event A has already occurred. Now that's called a conditional probability, and it's used to denote the probability that event B occurs given that A has already occurred. So now we have these definitions for dependent and independent events. Events A and B are said to be dependent if the probability of B given A does not equal the probability of B. In other words, A having occurred previously affects the probability of B occurring on the second trial. So this is what we mean by dependent events, and we'll look at some examples to clarify this in a moment. On the other hand, A and B are said to be independent events if the probability of B given that A has occurred equals the probability of B. So event A having occurred previously does not affect the probability of event B occurring on the second trial. So that's what we call independent events in that case. Now let's take a look at an example to clarify this. Now here we have 2 examples illustrating the difference between dependent and independent events. So in the first example, we have a bin that contains 10 balls numbered 0 through 9, and you randomly select one ball and write down its number, and then without replacing it, you reach into the bin and randomly select a second ball and write down its number. Now because of not replacing the first ball, if a 3 is drawn the first time, think of that as being like event A, then the probability of getting a 5 in the second trial, given that a 3 was already drawn, is going to be 1/9, right? Because a 3 is no longer in the bin. Now think of the 5 as being like the event B, and the 3 is like being the event A. Alright, so now you see the probability of a 5 given that a 3 was already drawn is 1/9, but that's not the same as just the probability of getting a 5, which would be 1/10 if you did not conduct the first trial. So in this case, we say the events of getting a 3, which is like event A, and getting a 5, which is like event B, are said to be dependent because the outcome of getting a 3 affects the outcome of getting a 5 on the second trial. And that's because this experiment was conducted without replacement. Now down here we have the same experiment, but what we do is this. We randomly select the first ball, write down its number, and then we replace it in the bin. And then we randomly select the second ball and write down its number. Now because of replacement, the probability of getting a 5 given that a 3 was previously drawn is still 1/10. Because after the 3 was selected the first time, you put that ball right back in the bin, so the bin still has 10 balls in it, numbered 0 through 9. So we see that the probability of a 5 given that a 3 was drawn the first time is still just the probability of a 5, which is 1 over 10. And that's because the first ball was replaced before drawing the second ball. So in this case, getting a 3 and getting a 5, like events A and B, are independent in this case. So now take note of this down here. In general, when experiments are conducted without replacement, you're going to have dependent events. And when experiments are conducted with replacement, you're going to have independent events. Let's take a look at another example. Now in this example, we're going to evaluate two conditional probabilities involving contingency tables. So for this problem, researchers in Pennsylvania asked students in grades 4 through 6 in 3 different school districts what they thought was the most important thing in school: making good grades, being popular, or excelling in sports. There were rural, suburban, and urban schools surveyed, and the table below lists the results. So down here we have our results. So in this table here, we see that there were in total 493 students surveyed. And if we look down this column right here, for example, the students from an urban school district, there were 181 of those students surveyed. 103 of them thought grades were most important, 52 thought being popular was most important, and 26 thought sports were most important. And we can also look across a row. For the students who thought sports were most important, 42 of them were from a rural school district, 22 were from a suburban school district, and 26 were from an urban school district, for a total of 90 out of 493 who thought sports were most important. Now let's take a look at these questions we have to answer. So the first question we want to answer is, if a student is selected at random, what is the probability that the student thinks being popular is most important, given that they are from a suburban school? And then part B, if a student is selected at random, what is the probability that the student is from an urban school, given that they think grades are most important? So let's see how we answer these two questions. So for the first part, we want to find the probability that the student thinks being popular is most important, given that the student is from a suburban school district. All right, so when we say that given the student is from a suburban school district, that restricts us to looking down this column, the suburban column. So now we know that we must be in this column somewhere. Now there were 159 total students surveyed from a suburban school district. And so the probability that the student thinks being popular is most important will then be 45 out of 159, and that is our probability. For the second part, we're given that the student thinks grades are most important. So that restricts us to considering only data in the grades row. So now we want to find the probability that the student is from an urban school, given that they think grades are most important. So we know that we are restricted to the grades row now. So there were a total of 255 students who think grades are most important. And so the probability that the student was from an urban school district is then going to be 103 out of 255. And that is our answer. So we see for these contingency table problems, the given part restricts us to either looking down a column or across a row. And that concludes our discussion about conditional probability.